Hello there. We are going to discuss detailed solutions of all the questions those were appeared in GATE 2009 with respect to analog circuit. These are the questions those were appeared in GATE 2009. If any question is missing, please let me know so that that question can be added here also. So coming to the question, the first question is question number 31. In this question, if you see a circuit is given where there is a voltage source, a current source, a diode is there, and there are two resistors. It is asked what is the voltage V across this 1 ohm resistor. What we will do, we will find out what is the voltage across this. Then we will see among the options which one is correct. Suppose Vd is the voltage across the diode or at this point, that is from this to this, the voltage is Vd. Suppose the diode is reverse bias at a particular time, then this will be acting as open circuited. This will be acting as open circuited. So if we redraw the circuit, then the circuit will be looking like this. Here if you see 1 ampere current is already in series with the circuit. So in the circuit, the current will always be fixed at 1 ampere. So if we apply KVL, then we can find out what is the value of Vd here. Vd will be equal to Vi minus 1 ohm into the 1 ampere current that is flowing through that resistor. So Vd will be Vi minus 1 volt. Now for the reverse bias to exist, this Vd has to be always greater than 0 or Vd has to be positive. That is this Vi minus 1 has to be greater than 0, so or Vi has to be greater than 1. So for the reverse bias to persist, Vd has to be greater than 0. That implies Vi minus 1 has to be greater than 0, so Vi has to be greater than 1 volt. So if this Vi voltage is greater than 1 volt, then the diode will be reverse biased and this voltage V will be 1. So if Vi is greater than 1, then the voltage V across this 1 ohm resistor is 1 volt. Now let us come to the case when the diode is forward biased, that is when the Vd voltage is less than 0, that is when the Vd voltage is negative, then the diode will be forward biased. When the diode is forward biased, that is Vd is negative. In that case what will happen? This Vi minus 1 will be less than 0, so Vi is less than 1. If Vi is less than 1, what will happen? If Vi is less than 1, the diode is forward biased, that means this is shorted, so this voltage or the voltage across this 1 ohm resistor will directly see what is the voltage Vi. So V will become equal to Vi when the diode is forward biased. So if we see, there are two conditions. One condition is when the diode is reverse biased, then in that case the voltage across this 1 ohm resistor is 1 volt, and the other condition is when the diode is forward biased. In that case the voltage across the 1 ohm resistor is the input voltage, that is Vi. So we have two conditions here. One is when the diode is reverse biased, the input voltage is greater than 1 volt. At that time the voltage across this 1 ohm resistor is 1 volt. And the other condition is when the diode is forward biased, in that case the input voltage is less than 1 volt, and the voltage that is V across the 1 ohm resistor is equal to the input voltage, that is Vi. So if we summarize both the condition, that is when the input voltage is less than 1 volt, the voltage V is equal to Vi, and when the input voltage is greater than 1 volt, V is equal to 1 volt. So what we will do, we will try to solve this by example. Suppose V, in one case we will take the input voltage to be let's say 4 volt. In that case, when the input voltage is 4 volt, it is falling under the second case. In that case, the voltage V will be equal to 1 volt. Let us take another example where the input voltage is 0.5 volt. In that case, it is falling under the first case, that is 0.5 volt is less than 1 volt. In that case, the voltage V across the 1 ohm resistor is equal to the input voltage, that is 0.5 volt. So if we observe both the cases, the voltage V is always the minimum between 1 volt and Vi. So V is equal to the minimum of the input voltage and 1 volt. So the voltage across the 1 ohm resistor is always the minimum voltage between 1 volt and the input voltage. Hence among the option Option A is the correct answer. The next question is question number 33. In this question, an unstable multivibrator circuit is given with op-amp configuration. We have to find out what property of the output voltage depend upon R2, whether it is related with the frequency or amplitude or both of them or neither of them. We will try to find out. In the unstable multivibrator, the op-amp will always act as a comparator, hence the output voltage will always switch between plus B side to minus B side. So if we take this non-inverting voltage as V plus and the inverting voltage as V minus, then the V plus voltage will be always equal to V0t into R4 divided by R3 plus R4. As I said, the output voltage is always switching between plus B side to minus B side. Let us assume at a particular time the output voltage is at plus B side. In that particular case, the V plus voltage will be equal to V sat into R4 by R3 plus R4. Let us say that voltage is V beta. Now as the output voltage is plus V sat, so through this resistor R1 and R2, this capacitor will also try to get charge, and this charging will continue till the V minus voltage is less than V beta value. Once the charging voltage exceeds the V beta value, then the output voltage will switch to minus V sat. So as I said, the capacitor will get charged via R1 and R2 resistor, and when the voltage Vc just exceeds the V beta value, in that case, as the op-amp is acting as a comparator, the output voltage will switch to minus V sat. Once the output voltage switch to minus V sat, in that case the V plus voltage will become minus V beta, and during that time, as the output voltage is minus V sat, the capacitor will try to discharge, and the discharge will continue till the capacitor voltage is reaching just about minus VV. During this point, as the output voltage is minus V sat, the capacitor voltage will try to discharge towards minus V sat, and once the capacitor voltage becomes just less than minus V beta, then the output voltage again switch to plus V sat, and again the cycle will continue. If we draw the voltage across the capacitor, then it will be switching between plus V beta and minus V beta. Suppose the voltage is initially at minus V beta, then it will try to charge towards plus V sat, but once it reaches plus V beta value, it will again starts to discharge towards minus V sat, but after reaching minus V beta value, it will again starts the charging process. So like this way it will swing between minus V beta value to plus V beta value. Suppose at time t equal to 0, the output voltage is equal to plus V sat, and the capacitor voltage Vc0 is equal to minus V beta. That is, suppose at this is equal to time t equal to 0. At that time, the capacitor voltage is at minus V beta value. Then the capacitor will try to charge towards plus V sat. So the final value it tries to achieve is plus V sat. So the final value will be plus V sat value, and if we write the capacitor voltage, then Vct will be equal to the final value, that is V sat minus within bracket final value plus V sat minus, that is the initial voltage is at minus V beta, so minus will be plus V beta e to the power minus t by R1 plus R2 C. Why R1 plus R2? Because as the capacitor will be charging through the R1 and R2 and both are in series, so it will be R1 plus R2. At time t equal to Tc, the capacitor voltage will reach plus V beta value. At that time, it will again try to discharge. So at time t equal to Tc, the capacitor voltage Vc of Tc is equal to plus V beta value. If we substitute this value here, we will get the corresponding time as the charging time, that is Tc. So by putting this, then we will get this expression, and from this we will get the expression of charging time, that is Tc, will be equal to R1 plus R2 into C, that is the capacitor value, ln of V sat plus V beta divided by V sat minus V beta. Now what we will try to do is we will replace this V beta value with the value that we have found out, that the V beta value is equal to, that is this V beta value. V beta is equal to V sat into R4 by R3 plus R4. Now we will replace this V beta value in that expression. So after replacing that V beta value here, we will get the expression that is the charging time in terms of R1, R2 and R3 and R4. Similarly, if we do the procedure for the discharging time, we will get the discharging time also, and the discharging time will be equal to the charging time. So we have the charging time, that is TC, which will be same as the discharging time. By doing the same procedure, we will get the discharging time also. So the total time period will become the twice of this value. Hence we can find out the frequency of oscillation is the inverse of the time period, which will be equal to 1 by 2 times R1 plus R2 C ln 1 plus 2 R4 by R3. And this frequency of oscillation will be the same for the output voltage also. So what we have the output voltage is switching between plus minus Vsat value, and the oscillating frequency of the output voltage is 1 by 2 R1 plus R2 C ln 1 plus 2 R4 by R3. So if we see the output voltage V output depends upon R2 only, the frequency, yes, the output voltage frequency is dependent upon R2. So first option can be correct. Second option, the output voltage is always switching between plus minus Vsat, that is its amplitude is independent of the value of R2. So second option is not correct, hence C is also not correct, D is also not correct. So we have only option A. So A is the correct answer. Next question is question number 34. In this question, it is given that the op-amp is ideal and the transistor has a VVE value of 0.6 volt. Its beta value is 150. Then we have to find out what is the type of feedback here, whether it is positive feedback or negative feedback, and what is the voltage here. Let us start by assuming the transistor is off. Once the transistor is off, there is no negative feedback, hence the op-amp will be acting as a comparator. So suppose the transistor is off, in that case the op-amp will act as a comparator, and if the transistor is off, then there is no current flowing through the transistor, so IC or IE value will be equal to 0, and once that is 0, this 10 voltage will directly appear across non-inverting terminal, and this 5 voltage appear across inverting terminal. So if V plus, that is here, the voltage that is V plus is 10 volt and V minus is 5 volt, then the output voltage will be plus Vsat, as it is acting as a comparator. Once this voltage is plus Vsat, to switch on the transistor we require only 0.6 volt, but this voltage is much greater than 0.6 volts, so the transistor will definitely on, and once the transistor will on, then it will provide negative feedback path through the resistance Re. Hence the op-amp will no more act as a comparator, it will be acting as an amplifier. So once the V is equal to plus Vsat, then the transistor will be on. If the transistor will be on, there will be a negative feedback through 1.4 kilo ohm resistor, and because of the negative feedback, the op-amp will operate in the linear region, that is it will be acting as an amplifier, it will no more saturate. So the virtual ground concept will apply here, because ideal op-amp is given, that means the gain is infinity, so V plus will be same as the V minus, hence the virtual ground concept come into play. So because of the virtual ground concept, V plus voltage will be equal to V minus voltage, that is 5 volt. Let IC is the current flowing through this 5 kilo ohm resistor, there won't be any current through the non-inverting terminal of the op-amp because of the high input impedance. So IC value will be equal to 10 minus 5 divided by 5, which will be equal to 1 milliampere. As beta value is very large, we can say that IE is very close to 1 milliampere. Then we can find out what is the voltage VE. VE will be equal to 1.4 volt. So as the transistor is on, this VV is equal to 0.6 volts, so this voltage will be equal to sum of VE plus 0.6 volt. Hence V equal to VVE plus VE, which is equal to 0.6 plus 1.4, that is 2 volt. So among the option, the voltage at the output of the op-amp will be 2 volt, and the feedback will be negative feedback that will be provided through the resistor 1.4 kilo ohm. So D option is the correct answer. Next question is question number 35. In this question, the VJT amplifier circuit is given, where small signal source with input voltage is applied to the transistor, and the transistor beta value is 150, and HI, that is the internal base resistance, is given as 3 kilo ohm, and we have to find out what is the output voltage among the 4 possible options. So if we see, this is the input voltage that is applied here at the input. It has two frequencies, that is 20 radian per second and another one is 10 to the power 6 radian per second. Now to this frequency, this capacitor will behave differently because its capacitive reactance value is given by 1 by omega c. So the reactance value will depend upon the input frequency value. So the reactance value is 1 by omega c. For omega 1 equal to 20 radian per second, the capacitance value will be 1 by omega 1 c. As the omega 1 value is very low, so the inverse value will be very high. That is, the reactance value of this capacitance will be very high. Hence, it will be acting as a open circuited. That means it will block the frequency of 20 radian per second. That is, this input voltage will be blocked. Coming to the second part, in the second input, omega 2 value is 10 to the power 6 radian per second. So in that case, as this omega 2 value is very high, so the inverse will be very low. Very low means it will be acting as a short circuited. So once it is short circuited, that means it will allow the input voltage to pass to the amplifier to be amplified. So this voltage will be blocked and this voltage will be amplified. Hence, this second part that is V sin 10 to the power 6t will be amplified. If we see, this is the normal formula, that is the gain of the amplifier is given by minus HFE RC divided by HI. HFC is nothing but the beta value, that is 150, and this HI value is 3 kilo ohm, and this RC in the circuit is also 3 kilo ohm. So the gain will become minus 150. So after substituting all this value, we will get the gain to be minus 150, and this gain will be multiplied with the input voltage. That is, this one is blocked, and with this input voltage it will be multiplied. So the output voltage will be the gain times the input voltage, that is minus 150 into B sin 10 to the power 6t. If we see among the option D is the correct answer. Next question, 57 and 58 are linked question. Here there is a CMOS circuit is given, one with one NMOS and one PMOS transistor, and it is given that the gate voltage Vg of the n MOSFET is increased from 0 while the gate voltage of P MOSFET is kept constant at 3 volt. Assume that for both the transistor, the magnitude of the threshold voltage is 1 volt. That is, the threshold voltage for this is 1 volt and for PMOS it is minus 1 volt, and the product of the transconductance and the W by L ratio, that is the Kn value, is given to be 1 milliampere volt inverse. So what we have to find out, for small increase in Vg beyond 1 volt, which of the following give the correct description of the region of operation? Vg beyond 1 volt, what is the region of operation of both the MOSFET? In the second question it is asked to find out the output voltage when the Vg is 1.5 volt. That is, we have to use the information of the first question to find out what is the output voltage. So what we have given here, given that this Vgn is slowly increasing from 0 volt, Vgp is 3 volt, the threshold voltage magnitude is 1 volt for both MOS, as well as the Kn and Kp value is 1 milliampere per volt square. So in the first question, when the Vg is increasing just above 1 volt, then we have to find out the region of operation of both the MOS. Now we have to remember few things. How to find out the region of operations when the NMOS and PMOS are connected in series. That is, when the ID current is same for both NMOS and PMOS. For NMOS, let's say VON is equal to VGS minus VT. Similarly for PMOS, VOP is equal to VGS minus VT. If this VON is equal in magnitude with VOP, then both will be in saturation region. And if this VON voltage magnitude is greater than the magnitude of this voltage, that is VOP, then the overdriven transistor, that is the NMOS will be overdriven, that will be in linear region and the other one will be in saturation region. Similarly, if the VON is less than VOP, then the PMOS transistor is overdriven, so it will operate in linear region and NMOS will operate in saturation region. It is to be remembered that the overdriven MOS, whether it is NMOS or PMOS, whichever is overdriven, that will be in linear region. Now let us come to the question. In the question it is given that for 57, the VG voltage is just increasing above 1 volt. Let's say VG voltage is 1.1 volt. In that case, VGS of N will be equal to 1.1 volt and VGS of N minus VTH of N. As VTH of N is given 1 volt, so we will get VGS minus VT will be equal to 0.1 volt. Next, for PMOS, the VGSP will be equal to 3 minus 5, because this is the source for PMOS and this is the gate for PMOS. So VGSP will be equal to 3 minus 5 is equal to minus 2 volt, and VGSP minus VTHP will be equal to minus 2 minus 1, because the threshold voltage of PMOS will be negative. So that's why 1 voltage magnitude is given. We will take minus 1 volt. So that will give us minus 1 volt. If we see in both the cases, now we will compare this Vn and Vp. Now if we compare the magnitude of Vp with Vn, the magnitude of Vp is greater than Vn. That means the PMOS transistor is overdriven. So if the PMOS is overdriven, that will be in linear region and the NMOS will be in saturation region. So if we see among the option will be NMOS will be in saturation region and PMOS will be in triode region. Triode region is nothing but the linear region. So D is the correct answer. Coming to the second part, we have to use the answer of the first part, that is NMOS is in saturation region and PMOS is in linear region. When the gate voltage is exactly 1.5 volt, then we have to find out what is the output voltage, VO. So here it is given that VG is 1.5 volt and the origin of operation of both the MOS is given. We have to find out what is the output voltage. If we apply the current equation for NMOS, then it will be equal to Kn by 2 VGS minus VT whole square, because it is in saturation region. So saturation current will be given by this expression, and this current will be equal to the IDP, that is the current equation for the PMOS transistor, which will be equal to Kp by 2 whole into 2 VGSP minus VTP whole into VDS minus VDS square. Here if you see, this current equation is because of the PMOS transistor is operating in the linear region. Now Kn and Kp value are given, Vg is given, Vt is given. We have to find out what is the VDS value. All the values are given except VDS, so we can find out what is the value of VDS by putting all other value. Here Kn and Kp will get cancelled. So by putting all the value, that is Vg equal to 1.5 volt minus 1 whole square, which is equal to 2 into VGSP, that is minus 2 volt minus 1 whole into VDSP minus VDSP whole square. After simplifying this, we will get a quadratic equation in this form. If we solve for VDSP, then we will have two values. Then we will check which one is the correct value or both are correct value. So by solving the quadratic equation, we will have VDSP value will be equal to one value will be equal to minus 1.866 and another value is minus 0.134. This VDSP is nothing but V0 minus 5 volt. V0 minus 5 volt will be equal to, that is V0 minus 5 volt will be equal to minus 1 plus minus root 3 by 2. By solving this, we will get the output voltage as 4.866 volt and another one is 3.134 volt. Now we will see which one is correct or both are correct. Coming to the first case, in this case the VDSP is minus 0.134 volt, which will yield the output voltage to be 4.866 volt. Now we will check the region of operation of this PMOS, whether it is lying in linear region in this case or not. For that we will find out what is the value of Vp. Vp will be equal to VGSP minus VTHP, which will be equal to minus 1 volt. Now in this case the VDSP is equal to minus 0.134 volt. So in this case, this VDSP value, that is minus 0.134 volt, is greater than this minus 1 volt. For the PMOS to be linear, this VDSP value has to be greater than this Vp value, and in this case the VDSP value is greater than the Vp value. That means this condition is satisfying. So hence, as the condition is satisfying, so the output voltage can be 4.866 volt or the output voltage can be 4 plus root 3 by 2 volt. In the second case, the output voltage is equal to 3.134 volt and the VDSP is minus 1.866 volt. Here minus 1.866 volt, that is minus 1.866 volt is less than this minus 1 volt, less than this minus 1 volt, that is less than Vp. So this condition is not satisfying the linear condition for the PMOS, hence this cannot be true. So as the condition is not satisfying, that is this condition leads to the saturation of PMOS, but the PMOS is operating in linear region in our problem. So the output voltage cannot be 3.14 volt, or the output voltage cannot be 4 minus root 3 by 2 volt. So the output voltage is 4 plus root 3 by 2 volt. If we see among the option D is having the value of 4 plus root 3 by 2 volt. Hence D is the correct answer. Thank you.